Yeah, dude.
What do you feel like? How do you feel?
I feel awesome.
Did it hurt?
No.
Do you feel smart?
Yeah.
Really?
Yeah.
Gravitation is relevation,
Late in March 2024, Neuralink's first human patient was introduced to the world. Ta-da! Nolan Arbog, at Modded Quad on X, spoke at length about his experience with the device from the press conference stage at Neuralink headquarters.
Hello, humans. I wanted to start this out with a joke, but I didn't think you lesser beings would understand.
Today, I'd like to highlight some key moments from his speech, talk about the progress the Neuralink team is making, and shed some light on the complexity of the task that lies ahead as they attempt to restore movement to paralyzed patients. Now, Neuralink is not the first brain-computer interface, or BCI for short, to enter human trials, nor will it be the last. Perhaps a basic overview of similar technologies will help us better appreciate what Neuralink is attempting to do. To date, there are several non-invasive BCIs that have been tested more extensively on humans. A device that does not require brain surgery or interface directly with brain matter can be approved much faster due to a lower level of inherent risk. One such device is Galea.
It can measure the user's heart, skin, muscles, eyes, and brain, and it combines that capability with head-mounted displays.
And as Connor Russo-Mano, founder and CEO of OpenBCI, Galea's parent company, points out in a recent TED Talk,
additionally, we're exploring the integration of non-invasive electrical neural stimulation as a feature.
External devices such as Galea are geared towards information gathering via a multitude of sensors. And although electrical neural stimulation would allow the device to send information back to the brain, they are at a disadvantage when compared to implants with direct brain tissue contact. Similarly, Kernel's Flow BCI, designed primarily to take in-depth readings of brain activity, is currently being used to study the effect of different chemicals and activities on the brain.
This is the power of flow. To better understand the effect of anything on the brain, we deserve better.
While external BCIs like these offer advantages such as non-invasiveness and accessibility, they are generally more limited in their ability to send and receive information to and from the brain due to several factors. These include the distance from the brain, which weakens signals and limits precision, potential signal interference and noise from various external sources, lower spatial resolution compared to invasive BCIs, which refers to the ability of a system to distinguish between different spatial locations or regions inside the brain with precision, reducing the ability to target specific neural circuits, constraints in biocompatibility and safety impacting sensor and stimulator design, and considerations for user comfort and wearability. In an attempt to overcome these limitations, implantable alternatives like Neuralink incur many other changes, not the least of which is literal surgery and its possible complications, such as infection and tissue damage. Neuralink and other companies like it must also consider long-term stability and reliability of implanted electrodes or sensors, which can degrade over time to tissue response or mechanical wear, risk of immune rejection or foreign body response to implanted materials, potential for invasive procedures to cause discomfort or psychological effects for the user, and ethical considerations regarding consent, privacy, and the potential for misuse of brain data. Frankly, this is an enormous challenge. But when the upside, improving the quality of life of many, many people, is so high, many companies are committed to finding a solution. One such company is BlackRock Neurotech, creators of the Utah Array, which already boasts 19 plus years of human studies, a track record of helping patients operate various games and communication software, and even restoring movement through robotic arms. The capabilities of this device are impressive, as demonstrated here by Bill Kokovar.
I'm still wowed every time I do something amazing. I ate a pretzel, I drank water.
This device consists of a small array of microelectrodes that can be implanted into the brain to record neural activity or deliver electrical stimulation. But as evident in Bill's demonstration, it is a wired device, limiting the mobility of the patient to some extent. The Utah array has 96 to 128 electrodes per array, where Neuralink contains more than 1,000 electrodes.
One day they had some mashed potatoes. Lo and behold, I was able to eat the mashed potatoes really well.
Since electrodes play a crucial role in facilitating communication between the brain, used for both recording neural activity and stimulating neurons, enabling bidirectional communication, a device with more of them will likely have more power and flexibility. The presence of more electrodes in a BCI system like Neuralink compared to known systems like the Utah array may have contributed to the challenge of gaining regulatory approval for human trials. The more complicated the device, the more questions to address about safety, biocompatibility, longevity, etc. With a novel design, another device named stentrode, made by the company Synchron, leveraged a pre-existing, minimally invasive procedure to implant their innovative version of a BCI.
Using the blood vessels as the natural highway into the brain and lacing the inside of the blood vessels with electrodes or sensors.
Stentrode technology effectively bridges the gap between external and implantable BCIs. They are minimally invasive devices, that is to say, do not require major brain surgery, but can still be positioned within a blood vessel in close proximity to the brain's motor cortex. They will gather information more effectively than an external device, but there is still a degree of separation between it and the brain tissue. Oh, and the term stent refers to a tiny tube placed inside a hollow structure in your body, such as a blood vessel in the brain. So these are very literally stent electrodes. Get it? Anyway.
By having a self-expanding nitinol scaffold, we're able to put it through a very small catheter.
The doctor is essentially directing a little robot worm from insertion point through the network of blood vessels in your head and neck until it arrives over top the motor cortex.
So it's on the end of a very floppy, long lead.
Unassuming though it may look, it is an incredible piece of technology.
Low in the neck, all the way up to the top of the head on the inside of the skull. And as soon as you achieve that, you get a great sense that we're on the way.
The long wire-like design also allows for information transmission to occur away from the main electrode array, which lessens the amount of activity occurring directly adjacent to brain tissue. Now, the stentrode team entered human trials before Neuralink, and I don't mean to devalue their work in any way by comparing their device to Neuralink, as it may indeed be life-changing, but only to illustrate how complex of an undertaking Neuralink has on their hands. Comparatively, Neuralink's device is larger, contains more electrodes in direct contact with brain matter, will transmit signals wirelessly from inside the skull, and of course requires brain surgery to be implanted. And here we have Nolan, a human being seeming alive and well with a functional Neuralink device. Other companies, such as Paradromics, have their sights set on similarly impressive, but even with their Connexus direct data interface, relies on an information sending and receiving module located further from the electrode array. Now, when I say Neuralink is trying to do something quite ambitious, you'll have a better grasp on why that is. And for such an ambitious device, entering clinical trials is an incredible achievement. That being said, we might also want to temper our expectations to some degree. In an article written by Liam Drew for Nature.com, several researchers expressed concern. The company is only sharing the bits that they want us to know about, says Samir Sheth, a neurosurgeon specializing in implanted neurotechnology at Baylor College of Medicine in Houston, Texas. There's a lot of concern in the community about that, which is true. We only see what we are permitted to see. But we cannot deny that by implanting a device of such impressive design, the Neuralink team has entered uncharted territory.
What would you say to the critics? Like the people who say what we're doing isn't novel or what we're doing is dangerous? What would you say to them?
Of course, Neuralink sought to diffuse the concerns of specialists and researchers.
What do they know? I mean, like, look at me. Outside of my handicap, do I look disabled?
Nolan had great things to say about the device, and elsewhere he assured the crowd that he had been made aware of the risks on top of having done his own research.
I'd read a lot of the negative stuff about this before the surgery. I realized how just wrong all of that is.
Don't get me wrong, Nolan's apparent success with the new implant is good news, but it is very early in the process. So far, we know his initial recovery has gone well.
Brain surgery was easy, man. I was expecting a much longer recovery time, and they kicked me out of the hospital like a day later.
I want to point out that the most common conditions that require brain surgery would imply a patient with compromised health, aneurysm or TBI, and or necessitate a procedure that is more invasive than Neuralink installation. Think tumor removal, and as a result, might necessitate the need for post-surgical monitoring. Nolan's brain is healthy, and aside from his paralysis, he is not otherwise injured, which contributes to him leaving the hospital so soon. So the fact remains, we don't know what his experience with Neuralink will look like in 1, 2, 3 or more years from now, or how others will fare with the procedure. From a public health and safety standpoint, it's far too early to say anything definitive. And I think that's probably what the critics are getting at. Now, in the same Nature article mentioned above, Dr. Bolu Ajiboye, BCI researcher at Case Western Reserve University in Cleveland, was quoted saying, "A human controlling a cursor is nothing new. The first human to receive a long-term BCI implant in 2004 could control a cursor with it, and non-human primates have been doing so for even longer," explains Ajiboye. Well, he's right. And the 2004 implant he's referring to is the BlackRock Utah array. And as we've already seen, its capabilities extend beyond simple cursor control. Remember Bill Kokovar and his bionic arm? But we've also previously established that this device has been less horsepower than Neuralink. Whether you're driving a Honda or a Formula One car, a rookie driver still needs to learn the rules of the road. It may be unrealistic to expect the first clinical patient to do much more than this in such a short period of time. This video was from Nolan's first day using the BCI. He is moving the on-screen cursor with his mind in order to click the targets. Since this type of cursor movement is possible with devices other than the Neuralink, a side-by-side comparison might help us to determine which device is more reactive or practical for patients. And possibly which device will be the first one to create present-day space marines. Nolan might be equally as pleased with, say, a stentrode implant or the Utah array. That said, with this presentation alone, Neuralink has shared a considerable amount of footage with the general public. You probably won't find much more from their competitors.
Whoa!
Sorry.
Granted, we don't know who else was competing for this world record or what BCIs they were wearing, but surely this is worth something. Neuralink also shared a video of Nolan playing Mario Kart with his father. If Neuralink's design allows for even a small degree of ease or practicality for the end user, then let's recognize their achievement. From there, Nolan progressed to playing Civilization, which is a turn-based strategy game. We're not at the action RPG stage quite yet. Again, I would venture to guess that anything capable of controlling a cursor could be retrofitted or programmed to control a game like this. Technically then, stentrode or the Utah array might also be calibrated to enable a person to do this, or even play Mario Kart. But let's be real. If Neuralink is the only company that decides to showcase their technology like this, they stand to captivate the public in a way that will lead to more support and likely more funding for their continued research. In the aforementioned Nature article, Dr. Ajiboye goes on to say, implanted high-density electrode systems developed by academic teams have enabled trial participants with paralysis to operate prosthetic robotic arms and hands and to communicate by decoding their imagined speech. He expects that Neuralink will soon be able to replicate some of these feats, but it's hard to know because there's very little information, he says. This makes me pose the question, with whom is Neuralink sharing information? This presentation gave me the sense that Neuralink is more interested in swaying public opinion than they are appealing to researchers in the field. If people are willing to support the company directly, they may not need as much support from governments, grants, etc., allowing them to operate autonomously. I think this is very important. There is a long, research-heavy road lying ahead of the Neuralink team. A quick look at the conclusion of Nolan's cursor calibration sequence will help. Consider what interaction between brain and computer are necessary in order to move that cursor freely. There are 8 targets organized in a circle and 1 more in the center. When Nolan imagines moving the cursor in a specific direction, the Neuralink device records the specific neural activity associated with that imagined movement. After calibrating in all directions, the device will have a unique movement map that allows it to interpret Nolan's intentions based on their neural activity and translate them into commands for controlling the cursor or other devices. That is to say, it will know the specific neural imprint associated with right, left, click, etc. Someone at the conference even asked Nolan directly, "What does it feel like to move the cursor with your mind?"
It's freaking wild. So much of what I feel is impossible to get others to understand.
But for the sake of science, let's try and wrap our heads around it.
I can feel myself moving my index finger. It's not moving, but I can feel it.
So far, as most of us are concerned, what Nolan is referring to here is equivalent to literal movement. In our experience, the intention to move initiates the firing of upper motor neurons in the brain, which send an electrical pulse down the spinal cord to the lower motor neuron that corresponds to the intended muscle. And voila, movement occurs. This happens so quickly that our control over our body feels instantaneous.
So there's a difference between like attempting to move it versus imagining to move it.
Right. So when we mentally rehearse an action, similar areas of the brain can light up as when we actually perform the action. This phenomenon is often referred to as mental stimulation or motor imagery. When we imagine performing an action, our brain activates the same neural networks involved in planning and executing that action. In Nolan, these things feel different because they are. But since the spinal cord is severed, they look outwardly the same. Functional MRI or fMRI studies have shown that when people engage in mental imagery or rehearsal, areas of the brain associated with motor planning and execution, such as the primary motor cortex and the supplementary motor area, become active. However, the intensity and pattern of activation may vary compared to actual execution of the action.
When I attempt to move something, it does feel like I'm moving it with, say, my hand or my wrist. When I first moved it just by thinking, it blew my mind.
So the Neuralink is sensitive enough to respond to imagined movements. Down the line, this will add a thick layer of complexity to the calibration process. We need a level of isolation between things we imagine and things we intend to do, lest I imagine banging my head against the wall only to end up with a TBI. Of course, so long as the patient is paralyzed, imagined movement and actual attempted movement may be practically synonymous. But the moment the device can facilitate more movement with, say, an exoskeleton that responds to the thoughts of the wearer, another level of nuance will become necessary. This is likely a long way off, but it is fascinating to consider nonetheless. And yes, an exoskeleton could be the next step towards curing paralysis. As mentioned earlier on, research involving prosthetic arms has already shown promise. Compared to calibrating the responsiveness of the Neuralink for movement of a cursor on a screen, moving a robot arm in space is infinitely more difficult as more dimensions of movement are introduced. Moving a full or even partial exoskeleton introduces another dimension of difficulty and will pose a challenge even for Neuralink's 1,000 plus electrodes. I think generally we take for granted the complexity of the processes that facilitate human movement, and any device that seeks to decode this process, which, mind you, would be unique, like a fingerprint in different patients' brains, will require a ton of research and development.
Literally only 12 BCI sessions so far, done 5 days a week, 8 hours a day. And for those of you who have worked in this field before, you know that this is not the usual thing.
Typically, according to the presenter, research typically happens much slower than this.
It's typically a couple days a week for a couple hours. By Monday morning, at usually around 11 a.m., we've usually surpassed what the normal is.
If Neuralink is able to safely implant the device in several patients as eager to contribute to the growing body of research as Nolan is, who knows how fast the team can progress or how quickly mind-blowing milestones will be reached. With every rocket launch, Elon's Mars by 2030 initiative seems less and less like a pipe dream. It isn't a far stretch to imagine him applying the same pressure in the world of BCIs. Overall, Nolan and the Neuralink team's presentation gave me a sense of hope. From what I have gathered through my research, their device is quite advanced and ambitious compared to other devices presently available. And while they may not be breaking new ground in terms of what BCIs are capable of doing, I did get the sense that they are eager to put in the work necessary to do so. Nolan strikes me as an excellent P1, and their research is off to what seems to be a great start. And while many of you might hate Elon Musk and anything with which he is associated, any research that moves the needle forward to restore function to those with spinal cord and motor neuron diseases is cause for hope. And I, for one, am really looking forward to the future to see what Neuralink can do for these problems, or others that I probably haven't even mentioned or thought of in this video. If you enjoyed the video, be sure to subscribe and give it a big thumbs up to feed the algorithm. And if you're already subscribed, make sure that YouTube didn't unsubscribe you from the channel, because they do that sometimes, bro. We're working towards 700,000 subs now, and we would love to have you with us on that journey. If you didn't like the video, be sure to let me know why in the comment section down below. I read as many comments as I can, and we use your feedback to make our videos better for you. And don't forget to follow my gym Human 2.0 Fitness for free right here on YouTube, where we post content that helps you move better and prevent injury. And if you simply want to support the channel, then consider becoming a member. Otherwise, as always, that's been a word from Dr. Chris, not your everyday ortho, where we see one, do one, teach one.